Hey everybody, this is going to be the fourth video. I'm just going to do a little bit of programming talking about heteroscedasticity and a little bit about fixed effects, or binary variables, categorical variables, whatever you want to call them. So the first thing I'm going to do is we're going to talk about heteroscedasticity. So I'm going to load in Stargazer so we can view our regression. So this is going to pop up as it always does. The next thing I'm going to do is I'm going to load up LM test and sandwich. I had mentioned them in the first video. If you have never used these things before, you will have to do install.packages, LM test, right? And then just run this. So if you hit control enter after highlighting it or just leaving your cursor here, control enter, it will run it. I'm not going to do it because I've already done it in the past. So I know that these library functions will work. But once I do that, maybe a loading bar pops up, maybe a bunch of other writing pops up, but it'll install and it'll say successful or unsuccessful, in which case just email me and we'll figure it out. But if it works perfectly and says installed successfully, beautiful, then you can just use these library functions. So if I do this, it will load some other required things. And then I'll load sandwich and nothing pops up apparently. And then we should have our environment set up. So I can also hit clear my environment in case I had some stuff here, but I'm going to pop open this little section of code here. So I'm just going to create some random data, plot it, do some super basic regressions, and just look at what happens when we correct for heteroscedasticity or when we don't. So the first thing I'm going to do is I'm going to create a sample type of 500. I'm going to create a data set called stuff. It's going to just be 500 normally just random 500 draws from a standard normal distribution. And we can kind of take a look at that right now. And it's just random data, right? Just random numbers, makes a uniform, a normal distribution, mean 0, standard deviation of 1. So the first thing I'm going to do is I'm going to create a y variable that's going to be stuff x. So it's just going to be 1 times that with no intercept, right? If I wanted to put an intercept, I could just do 10. Then I'm going to have a 0 intercept, a coefficient of 1, and then an error term, which is going to be 500 random draws from a normal distribution with a mean 0 and standard deviation of 1. So I'm just going to skip a little bit and just plot that relationship so we can kind of take a look at it. I'm going to open up this a little bit more. So if I plot this relationship, if I plot x and y, I'll get a relationship that looks like this. And you can kind of see that there's clearly a positive relationship here. It just looks like it. So yeah. This next one is going to be the same exact coefficients. So intercept of 0, a slope of 1, and an error term that now has a mean 0, but a standard deviation of 5. So if I run this one, now pretty much what I'm having is I'm having more variability in my data. So it should be more of a cloud and less of like a pulled out string kind of. So if I plot these two together, we can see again, it's definitely more of a cloud. There's more variance going on here. Now this third one, this y3, can be the same exact regression equation, but now the regression is going to depend on my x variable. So my variance is going to be 5 plus whatever this data is. So if I look at this, it looks like it goes from, here's a 2.3 is pretty large, negative 1.7. So it goes from about -3 to +3. So my variance is going to be directly related to my x. So if I run this guy and I plot it, we can see kind of a cone shape. So we can kind of see that it starts to kind of blow up a little bit towards as x gets larger. So effectively, we're just making a pretty typical cone shape heteroscedasticity, right? So this next one I'm going to do is I'm going to make the variance of the error term depend on the absolute value of x. So if I run this, we get only positive numbers. So pretty much as you get away from 0, the variance is going to increase. So if I run this one and I plot it, you can see that the variance is very, very small right here, but gets wider as you get away from 0, right? So this is also heteroskedasticity. Again, I can actually specify exactly what my heteroskedasticity is going to look like, but in typical cases, you actually can't tell this, right? But this is not an unfeasible thing to see, or something that you would be surprised to see in the real world. Data that has larger values maybe have larger variances, right? So now that I've plotted all of them, I'm just going to run a regression each y on x. So if I just run each one of those, the first thing I can do is I can just do Stargazer and just take a look at them. So each one of them, this first one is going to be constant should be roughly equal to 0 because it doesn't have stars next to it or it's insignificant. We cannot tell this different from 0. So effectively, this and this are pretty much exactly the same. However, this is the coefficient that I'm estimating, so it gives me a 0.9, and it gives me a standard error that's relatively small. This next one is giving me a 0.731, which is giving me a quite a bit larger standard error, but relatively similar coefficient, maybe a little bit smaller, a little bit lower than this one, but also a much larger standard error. Next one also has a pretty large standard error and a pretty large estimate here. And this one has a pretty large estimate, pretty much close to 1 though, with actually a standard error in between both these guys and this guy. So what I'm going to do now is I'm going to implement these robust standard errors, these heteroskedasticity robust standard errors. So I'm going to comment out these 4 regressions. I'm going to uncomment these 4 regressions. Oops. So if you remember from the code in the slide, all you have to do is do coef test, put the name of the regression, comma, vcovhc. And this will do your heteroskedasticity, your robust standard errors. So if I run just this line, it will give me something that looks just like a regression, just like a summary table. In fact, if I just do summary of reg 3, we can see that it's pretty much just taking this, but it's changing not this, but the standard errors are different. So see how this one went from 0.325. This is the regular OLS, and this is the heteroskedastic robust standard errors. So they grew very, very slightly. In fact, almost not at all. But anyway, I'm going to run this Stargazer, and Stargazer will take the data that's here and format it so it looks nice like this. So if we run this, we now get our data looks like this. We don't get any of the extra stuff here, like our sample size and our fstat and r-squared and all that stuff. But don't worry about it for now. There are ways to get it back. It's fine. So if we recall the other ones, so if I just look at these guys, this had a 0.972 and a 0.042. If we go back over here, this standard error actually decreased when I use robust standard errors. So that can happen. Sometimes it can actually go down, but relatively this remained unchanged. This standard error almost, I would even argue, didn't change at all. Now, if we look at this one here, 0.731 and 0.237, we can see that from this one, it was 0.22 or 0.228, 0.237. So this one increased slightly. Again, the estimate did not change. It shouldn't. This is only standard error corrections. This one went to 0.256. It was 0.236 before. So again, it increased by kind of the same magnitude, maybe about 0.2. This one also increased by about 0.1 or 0.2. And then lastly, this one right here. This one seemed to increase actually pretty dramatically, almost double the standard error. So the standard error before was 0.139, and now it's 0.255. So we can see clearly there was some sort of miscalculation going on with these ones, or some sort of bias in the standard error estimates. And if my variable, if my slope was a little bit smaller, for example, I can change it to maybe 0.5. I can plot it again. You can see it looks like this now. Now I know that there's a true effect of 0.5. And if I run this regression, I'm just going to put it so we only see both regression 4s. So this is going to be regression 4 and then regression 4 with the heteroscedastic standard errors. If you look at this now, oops, maybe I can do a little bit more than 0.5. Maybe I can do 0.8. Well, I was trying to get it so it was significant here and insignificant here, but you can see that if the number is, this can make this increase in standard error can change the significance of a variable. And again, that has some pros and some cons, but it's something that we have to do, and it's correct. So moving on from standard error corrections, I want to talk a little bit about dummy variables or categorical variables. So what I'm going to do is I'm going to create 5,000 a data set of 5,000 observations. I was going to do states originally, but I'm just going to create fake states. So now my states are just going to look like this. Oops. So now my states are just going to look like this, where it's state 1, state 2, state 3. And I'm just going to create a data set that looks like this. So I'm going to create a data set of salary, the state. So I'm just going to sample these states just randomly. I'm going to create this random ability that's going to be a uniform distribution from 0 to 10. So you can think of ability however you want, some sort of measurement for some skill or something like that. Just pretend that it matters or it's quantifiable. This last one is going to be college, whether or not somebody went to college. So I'm going to run that. So now if we open up work, we can kind of take a look at what our data looks like. We have the different states that people are from. We have their varying abilities. We have differences in whether or not somebody went to college. And what I'm going to do now is I'm going to create salary as a function of all of these things. So when we run a regression, we can go back and we can take a look and say, okay, how much does the regression results mirror how I created the data? So our salary variable is going to be 20 times your ability. So whatever your ability is going to be times 20 of that. 5 times ability times college. So if you so you're worth $20 per level of ability, per 1 unit of ability. But if you go to college, you're worth 25 per unit of ability, right? So this is the added benefit of going to college. And then I'm going to each state. So if you're state number 1, you're going to make $5. If you're state number 2, you're going to make $10. If you're state number 3, you're going to make $15. So each state, just for some reason, there's some sort of minimum wage law that is increasing wages for everybody who works in that state, or maybe there's some sort of there's something that's driving up salaries in that state. We don't know what it is, but it's there, right? So these are things that you might want to control for. And then just an error term here. So now what I'm going to do, and I didn't do this before, but I'm going to change the ability to reflect what state they're from. So for example, while salary can be different just for different states, for example, maybe places in New York. So in New York, I think the minimum wage is, I think, creeping up to $15, if not already there. In the city, it might actually be 15, whereas in West Virginia, it's certainly not 15. It might not even be 9. I'm not actually sure. But there are differences in minimum wage laws, so differences in salaries, obviously. There could also be differences in ability. For example, if you're a hockey player and you come from Russia versus you come from Houston, Texas, there might just be differences in average ability in hockey if you come from Houston versus if you come from Russia or Canada. That's just a fact. And we want to be able to control for that, right? We want to change the ability relative to where you come from. So if we do this, we can plot work and ability, right? Or sorry, ability and salary. So if we plot these two things, we get this sort of distribution. So even though I said that salary should be positively correlated with ability, for some reason we're getting this negative relationship, right? If we told the regression to find the line of best fit, it would run a regression straight through this, right? A negative slope right through this. In fact, if I just do this regression and I do summary of reg 1, we get a -4. So each unit of ability increase is going to decrease salary by 4, right? And it's pretty significant too. So the regression is very, very confident in this. But however, if we plot the work and salary, or the ability and salary relationship, and we color the observations by what state they're from, so it's going to make some sort of random rainbow pattern. And if we plot it like that, oops. If we plot it like this, we're going to get something that looks like this. So you can see each state is going to be its own color. So you can see that ability and salary are actually positively correlated, right? There's a positive correlation. If I just looked at just this first state, if I just looked at state number 1, I would actually get a positive correlation. So if I do that, I can actually do work, right? Where work state equals state 1. And if I run that summary, I get now a positive correlation, right? I get an average of 22, which is pretty much in between 20 and 25. So on average, we get a 22.5 increase in salary if I just use that one state. However, I have a ton of different states, so I want to use all of them. So how can I do that? Well, I have to use something called fixed effects. So the way I'm going to do it is I'm going to put a binary variable for each state. Now, luckily, R will do this for us. So if I just put in state here, and because I have it as being a text value, it will know that each one of these things needs to be its own variable. So I'm just going to run regression 3 really quickly. And if I do summary of regression 3, oops, it's going to output all of these extra coefficients. These extra coefficients are going to be the binary variables or the fixed effects for each individual state relative to the control or the omitted category, the omitted group. And if we look briefly, we can kind of actually tell that the omitted group is just state 1. So we know that as we increase, each one should be an increase of 5 units. So state 2 is going to be an increase of 2.7. State 3 is going to be 5.3, right? So you can see that there's some sort of positive relationship between state and salary. And if we control for it and we look at the effective ability, we get that 2.24, right? So right between 20 and 25. So when you are including this, you're controlling for differences both in salary, but also in ability. So there's differences in ability clearly, right? Like this red one has on average lower abilities than these lighter ones over here. So when I'm using fixed effects, I'm controlling for the differences in ability here and here, and in salary for here and here, right? So I can kind of come up with a more exact relationship. And then finally, I can run all three of these, use Stargazer to view the entire thing, and we can come up with some estimates for what I had. And we can also do robust standard errors here. So if I wanted to do reg4 v HC, right? So I'll just comment out these guys so we can just look at this. So if I wanted to go from regression 4 to regression 4, but with heteroscedastic robust standard errors, I can run both of these. And we can see that the standard errors don't change all that much, even though this does increase slightly. This actually decreases a little bit. This decreases a little bit. This increases a little bit. And none of our estimates change. So that's pretty much how you would use robust standard errors. That's how you would use fixed effects in this model in this way. I hope to go over a little bit more of this in class or during office hours, but hopefully this is a good start for that.